All right, so today we're diving deep into the world of Julian Schwinger.
Oh, a fascinating choice.
I know, right? And to guide us, we've got this essay by Jurgo Schneepat. It really digs into Schwinger's life and his work, all the way to how he's impacted, modern quantum technology.
Schneepat really gets it, Not just, how brilliant Schwinger was, but the elegance of his thinking. It's a real treat, especially if you're into physics.
Definitely. So Schneepat kicks things off with, a little bio. Julian Schwinger, born 1918, New York City.
And a total prodigy, right? Schneepat even mentions how Schwinger was publishing physics papers while still an undergrad.
Yeah, incredible. And that, of course, led him to Columbia University, where he studied with, get this, another Nobel Prize winner, Isidore Isaac Rabi.
It makes you think even the greatest minds have those mentors, those figures who shape their path.
Absolutely. And so we've got young Schwinger on this, path to greatness, and then boom, World War II.
And Schneepat really points out how that wasn't just a sidestep, but a crucial part of Schwinger's development. Working at MIT's radiation lab, all that radar technology.
You have to wonder how being surrounded by, the top physics minds, all focused on these super urgent problems, how that might have shaped him.
It's Schneepat suggests that this experience grounded his later theoretical work. Pure academia might not have had the same impact.
Makes you think. But let's shift gears a bit. It's the 1940s, and this is where Schwinger really makes his mark, particularly with quantum electrodynamics, right?
QED.
Yeah.
And Schneepat sets the scene so well. The existing theories, about light and matter interacting, they were giving these nonsensical infinities.
Yeah, in physics, infinity usually means something's gone wrong.
Totally. It's like a big flashing sign saying, your theory's broken.
So how did they even begin to tackle this? I know Schneepat mentions Feynman and Tominaga alongside Schwinger, all crucial for this, QED revolution.
It's fascinating, right? Schneepat talks about how each of them had their own unique way of looking at it, but they all reached a solution that completely changed QED. And Schwinger, he brought this incredible mathematical rigor. Schneepat emphasizes his use of the Lagrange formalism, super powerful for describing how systems change over time.
So he's bringing the big guns, mathematically speaking, to solve this.
Absolutely.
But can you give me an example of how Schwinger's contributions were different from, Feynman or Tominaga? What set him apart?
Well, Schneepat highlights this idea of renormalization. It was Schwinger's way of handling those pesky infinities that were plaguing the older theories. Almost like, cleaning up the mathematical mess to get to the meaningful results.
So taming the infinities and making actual, testable predictions. But didn't he also have that one calculation, the one that really cemented his place in physics? Something to do with the electron, right?
You're talking about the anomalous magnetic moment of the electron. The older theories just couldn't get it quite right, but Schneepat explains how Schwinger calculated it with incredible precision. And boom, it perfectly matched the experimental results. A huge win for QED. It was a big part of why he got the Nobel Prize in 1965, sharing it with Feynman and Tominaga.
Amazing.
Truly remarkable work.
Absolutely. All right, so picking up where we left off with Schwinger, his contributions to QED were, mind-blowing. But this deep dive, it wouldn't be complete without looking at how he did it, the methods that made him so unique.
Totally. And what I love is how Schneepat, he doesn't just tell us what Schwinger found, but kind of pulls back the curtain on his thinking, the elegance of it.
Yeah, let's talk about that machinery. Last time we touched on the action principle and how Schwinger used it for quantum fields.
And right. Remember in classical physics how we often talk about a particle's path? Well, Schwinger, he focused on the action of the whole system. It's a way to measure how the system changes over time, mathematically speaking.
Okay, that's coming back to me. But then Schneepat throws in these functional integrals, and they always sound so complex.
Oh, they are. But they're also incredibly beautiful. Think about it. You're trying to, say, predict where a particle will end up. Classically, you'd calculate its path, right? Single trajectory.
Makes sense.
But in the quantum world, it's like the particle takes every path at once, each with its own probability.
Yeah, that's the part my brain kind of short circuits on.
I know, right? It's counterintuitive, but that's where the functional integrals come in. Schneepat explains how they give you the math tools to add up all those possible paths, weighted by their, likelihood.
So he's making sense of this, almost paradox, the particle doing everything at the same time.
Exactly. And Schneepat makes it clear this wasn't just a math trick. Functional integrals became, the way to do quantum field theory. They let us make incredibly precise predictions.
I'm seeing why Schneepat's so impressed. But there's another piece here, operator methods. Honestly, I got a bit lost last time we mentioned those.
No worries, let's break it down. So in quantum mechanics, we use quantum states to describe stuff. It's like a snapshot of, say, a particle's properties, its energy, its momentum, all that.
Right, so the state tells us what the particle's like at a given moment.
Yeah, and then operators, they're like the verbs. They describe the actions, the transformations that can happen to those states. Like an operator might describe a particle absorbing a photon, changing its energy level.
Ah, okay, so they act on the states, like instructions.
Exactly. Now, Schwinger, he did something amazing. Schneppat explains how he basically came up with an algebra for these operators. Rules for how they combine, how they act on each other. This let him analyze really complex systems like the electromagnetic field itself in a whole new way.
Hold on, so instead of the electromagnetic field being this classical wave, he's describing it with quantum operators.
Exactly. He's quantizing it, bringing it into the quantum world. And this operator approach, Schneppat argues, it was huge, especially combined with Schwinger's work on the action principle and all those functional integrals. It revolutionized how we understand QED.
This is all fascinating, but I have to admit, part of me is thinking, why should I care in 2025? Like, how does this super theoretical stuff connect to my life?
I get it. And that's where it gets really exciting. Because Schneppat makes it clear. Schwinger's work wasn't just some abstract math game. It laid the groundwork for the quantum technology we're seeing explode right now.
Wait, really? So the map he was doing is helping build the tech of the future?
Totally. Think about quantum computers. They use these things called qubits, right? And they can be in the superposition both 0 and 1 at the same time. But to control those qubits, you need to understand how they interact, how their quantum states work.
Okay, I see where you're going with this.
Right. Schneppat lays it out. Schwinger's theories about quantum fields, about interactions, that's the foundation for how we even build these qubits, how we control them, how we design the algorithms.
So he gave us the toolbox, and now we're using it to build these incredible machines.
Exactly. And it's not just computers. Schneppat mentions quantum sensors, too. They use the supersensitivity of quantum states to make ridiculously precise measurements.
Give me an example.
Well, think about atomic clocks. Super important for GPS, right? Their accuracy depends on understanding those tiny atomic energy levels, the transitions. All stuff that Schwinger's work on QED helped clarify.
So it's not just theory, it's directly feeding into making this tech better.
Right. And it goes beyond clocks. Schneppat even points out that Schwinger's calculations of, remember, the electron's magnetic moment, those are crucial for building supersensitive magnetometers, used for everything from medical imaging to finding minerals underground.
Wow, so we're talking about real-world application stuff that's already affecting us.
Absolutely. And honestly, as Schneppat suggests, this is just the beginning. As quantum tech keeps advancing, Schwinger's legacy is going to become even more apparent.
I'm definitely ready to explore more of that legacy. Welcome back to our deep dive on Julian Schwinger. We've seen how he revolutionized QED and how that's shaping quantum tech today.
And now, Jorgo Schneppat takes us into the later part of Schwinger's career, where he didn't exactly slow down.
He didn't just, rest on his Nobel laurels.
Not a chance. Schneppat describes him diving into even more complex areas, particularly something called non-abelian gauge theories.
You might have to break that one down for me.
Sure. So think about the fundamental forces, right? Electromagnetism, the strong force holding atoms together, the weak force behind radioactive decay. They're all described by quantum fields.
Okay, got it.
Well, non-abelian gauge theories, they're a way to describe those fields even more powerfully, especially when, multiple forces are interacting.
So it's like he took his QED work, how light and matter interact, and went even deeper to the fundamental forces themselves.
Exactly. And Schneppat highlights how Schwinger was fascinated by symmetry in physics. These non-abelian theories, they have special symmetries that are essential for understanding how particles and forces behave.
Symmetry, it's all about patterns, right?
Yeah.
Underlying structure. Makes sense to be crucial for, the laws of physics.
Right. And Schneppat even suggests that Schwinger's work here paved the way for later breakthroughs in particle physics, specifically the development of the Standard Model, our best current understanding of, the fundamental building blocks of matter.
Wow, so even later in his career, still shaping the whole field. But Schneppat also talks a lot about Schwinger as a teacher. What was it about his style that made him so influential?
Well, Schneppat uses this term, the Schwinger School. It wasn't just what he taught, but his whole philosophy.
What made it unique?
He really instilled in his students this deep appreciation for mathematical rigor, for elegance. Schneppat even quotes Schwinger saying that the most beautiful equations, they often hold the deepest truths about the universe. Like the search for beauty was a guide to understanding the laws of nature.
That's beautiful. More than just solving problems, it's finding the beauty in the solution.
Exactly. And Schneeppert points out how much this resonated with his students. Many of them went on to make huge contributions themselves.
Any examples? Who was part of this Schwinger school?
Oh, absolutely. Schneeppert mentions Sidney Coleman, brilliant theoretical physicist, known for his work on, you guessed it, quantum field theory. And then there's Sheldon Glashow, one of the architects of the Standard Model itself. Just two examples of many who were influenced by Schwinger.
Wow, it's amazing how one person's teaching can ripple outwards like that, shaping minds, influencing the course of, scientific progress.
It's a testament to mentorship, right? And Schneeppert even argues that it goes beyond those directly taught by Schwinger. His ideas, his methods, they've permeated so many areas of physics, from condensed matter physics, studying how matter behaves, all the way to string theory.
So safe to say his work is still very much alive today.
Absolutely. And Schneeppert's essay really drives that home. Julian Schwinger, he wasn't just brilliant, he was a visionary, laying the foundation for so much we see today. It's mind-blowing that theories he developed, decades ago are now being used to build quantum computers, super-sensitive sensors to explore the very fabric of reality.
It makes you think about how important basic research is, right? Those unpredictable ways science shapes the future.
Couldn't agree more.
Well, this has been an incredible journey. From QED to quantum tech, from the beauty of his math to his legacy as a teacher, Julian Schwinger truly left his mark.
It's been a pleasure exploring it all with you. Seriously, everyone should check out Schneeppert's essay. It's enlightening.
Absolutely. And I think a key takeaway here is that power of curiosity, that relentless pursuit of knowledge. Schwinger's life, his work, it's an inspiration for anyone who wants to understand the universe.
Perfectly said.
So that wraps up our deep dive. Thanks for joining us, and until next time, keep exploring, keep questioning, and keep diving deep.